differencing instead of non-seasonal difference. So with seasonal data, which is non-stationary, it may be appropriate to take seasonal differences. Seasonal differencing is the difference between an observation and the corresponding observation from the previous year. So 1 minus, instead of 1 minus L, so we apply 1 minus L to the power of S. So let's say you have quantity data and you add to 4, so meaning that we take difference between YT minus YT minus 4. If you say quantity data, so we take difference, we apply the differencing, so we take difference between the same any quarter of this year minus the same quarter last year for observation per year. So YT minus YT minus 4. Or for the case of monthly data, so we take difference S equal to 12. So monthly data S equal to 12, 1 minus L squared. So L 1 minus L 12 on YT becomes YT minus S. YT minus 12. Okay, so meaning that we take difference between the same month this year and the previous year. So January this year minus January last year, February this year minus February last year, and so on. So that will be called as difference. So which is the change between observations separated by S period, either dependent, so whether quarterly or monthly or weekly. So we add S the number of season, for monthly data S equal to 12, for quarterly data S equal to 4, for weekly normally we have 52, weekly data 52, and so on. So as with non-seasonal differences, the differencing can be repeated to obtain seasonal, to obtain second order seasonal differencing, although it is rarely needed. So if let's say the series or after you apply seasonal differencing, the series still not necessary, so you can further apply, you can apply further differencing. But normally what we do, if after you apply the seasonal difference, the series, the transform series, the difference series still not stationary, so we apply non-seasonal difference. For second difference, we apply second non-seasonal difference instead of the seasonal difference. So normally we just apply one seasonal difference. Normally we just apply one. So if the series or have still not stationary, we apply another difference, but non-seasonal difference. So when both seasonal and first difference are applied, so first difference refers to non-seasonal and normal, just the usual normal differencing if you cut current and previous values. So that one, the first difference. Apply if no difference, which is done first, the result will be the same. However, it is recommended that seasonal differencing be done first because sometimes the resulting series will be stationary and there will be no need for further differencing. So you can apply both, but you are encouraged to apply seasonal difference first before you apply non-seasonal difference. If you apply both, the final series that is going to be exactly the same. Okay, the different series, you apply both seasonal difference plus, so this one, you take difference between, let's say you have monthly data, you apply difference, you calculate difference between the same month this year and last year, and then after that you calculate, you take non-seasonal difference, meaning that the difference between two values of different values. So I mean, after it doesn't matter which one you apply first, the last what we call it transform, or the different values is going to be the same. Doesn't matter you apply the non-seasonal difference or seasonal difference first, or you apply seasonal difference first, or you apply non-seasonal difference. The values is going to be exactly the same. However, you are encouraged to apply seasonal difference first because the chance for you to get stationary series after first difference, after you apply seasonal difference, is higher than if you apply non-seasonal difference first, if the series has seasonal variation. If the series has seasonal variation, then again you are encouraged, it is recommended to seasonal difference to be done first, because sometimes after you apply seasonal difference, it's already stationary, then no need to apply to the differencing. Okay. So example of data that we have, the electricity monthly data production data. So we have data here in this one. So in Spectrum, I provide the reviews command. So at the same time, we can just do this one. So this one, not this one. Reviews. Okay, so how to know whether this has seasonal variation? There are a number of possible ways for you to identify, to examine whether the series has seasonal variation. One of the method is by using the technique that you done before in the earlier topic, in the earlier lecture, by conducting the what we call the walk test, testing. So you can based on you can estimate the regression model and then you perform test. The regression model is in the dummies, and then you perform tests in order to identify if the series has seasonal variation. So that can be done one of the possible ways. Okay, so you have the data. So if you electricity data, so this one, if you produce graph, so you identify, you see that it seems that it has trend, and then it looks like it has seasonal variation. Then in order to identify or to confirm that it has seasonal variation or not, then you can perform the test, the one that we started before. Okay, so you estimate regression model. So let's say it has trend, it has seasonal variation. So this one just using regression model. So meaning that we add a time trend, normal intercept, the common intercept, and then say dummies, but we drop one because we have C. If you want to include all dummies for all seasons, then you have to exclude C. This one we discussed before. Okay, so you can perform the test to give you an idea whether this is a variation or not. You can perform the test. You are testing the coefficient, because we have C in the model, remember, so the way that we perform the test, we need to test whether all these, the coefficient for the true coefficient for all these dummy equal to 0 or not equal to 0. Okay, not equal but equal to 0 because you understand this one we discussed before. Okay, and I'm going to explain again. So we perform the walk test. So the conclusion we can make is that there is seasonal variation. So meaning that if you want to construct Arima model, it should be seasonal Arima. Okay, so it has seasonal variation. Another approach is that another method is by checking the cologram. The cologram sometimes able to show whether, if it's in a variation, it's able to show the pattern. So this is data. So if you produce cologram, you have something like this. So cologram for the series, you go to view. Not this one, the series. Okay, so the series view time to diagnostic cologram level, not vertical level, or in a series. Yeah. So how to know if there is seasonal variation in the series? You need to check the sample autocorrelation at lag S and the multiplication of S. So for example, the data that we have now is the monthly data, so you have to check at lag 12, 24, 36 and so on. So, okay, let's say we reproduce by adding lag, let's say you put 48, meaning that for 4 years. Okay, 48 or even 60 also can. Okay, so you see at lag, because this monthly data, so you see at lag 12, you see that the sample autocorrelation, the value of sample autocorrelation higher than the nearby correlation lags. And then the same happened for lag 24, 36, 48. You can see the pattern. Okay, for lag S, 2 times S, 3 times S, you can see the pattern, the autocorrelation value, sample autocorrelation higher than the adjacent. So this is actually indication for the present of the seasonal variation in the series. So this is another way lah. Okay, another way for us to detect. First, maybe you can just look at the graph. The graph you can see lah the pattern. Okay, and then you can perform health testing, but based on the regression model, or you also can look at the program lah. Okay. Program. So now the series has seasonal variation. So the series show a trend and a very pronounced seasonal pattern. So the trend, okay, this one, the trend increasing, and then the autocorrelation illustrates clearly that the series is non-specially. There is the value of autocorrelation still large. Okay, this is based on the program. Also, sometimes we are able to see that. I mean, remember last week we discussed one of the typical pattern of the sample autocorrelation. If the series is non-specially, then the value of the sample autocorrelation decrease slowly. Okay, or then decrease slowly. So that's another indication. But to confirm that, you can perform unit test. Okay, perform unit test in order to identify if the series is stationary or not. Okay. The series is seasonal because the value of the autocorrelation at lag 12, 24, and the series are all larger than the adjacent autocorrelation, just like the one that I mentioned just now. And therefore, we apply the signal differencing on the series. Okay, so in order to remove the unit root, to make the series stationary. So basically, what we apply is we remove the seasonal unit root. Okay, so basically there are other alternative tests for the case of seasonal the data has seasonal variation, but I think the one that available in use actually for the case of I mean the one that we have is not very one. I mean there are other tests available that can be used to detect for seasonal unit root, but that's not available in use. So we just use the one that we have in use. Okay. So you just perform the ADF, KPSS test, or even PP test later on. So this one, so we have already identified that the series has seasonal variation, and then to confirm whether it has trend or not, to confirm whether it is stationary or not, you can perform unit test. Okay, so you can just perform unit test as usual, just like how we did last week. So you go to view, time series diagnostic, unit test, standard unit test. So this one you use 14, maybe slightly different display. The one that you have, I think perhaps still 13, it is 13. So perform the test. So level, remember that ESL, the one that we discussed before, there are 3 equations. So you need to perform test on level in order to identify if the series is stationary or not. You perform using all the 3 equations, and then if all still the same conclusion, then it is easier for you to make conclusion. If the 3 different conclusion, then you have to refer to the one to any of these. Okay, one of the possible way to decide which one you should refer is by looking at AIC and SIC. But that one is the way, but it's not the best way. Sometimes, so later maybe, I mean, for the exercise that we have one example, I think using AIC is also not actually, I mean, certain case, so it's not really the best way. So perhaps you should, I mean, it's also useful if you also take into account other factors or other information. For example, by looking at the graph as well, in order to decide which equation that we should use. Okay. Okay, so perform the test tadi juga lah. So let's say none, I mean the result already given. I will provide result in the Word file to save time lah. Okay, but this one just like how we did last week. So we perform the test to check for the level of the series whether it's steady or not using any actor, for example. Then I perform the three equation. For example lah, if let's say intercept this one, you get the result and you complete as usual. So I provide the result of any test here. For example, 1. So for the level, based on the p-value, based on p-value, I mean in this case, if you compare all the three equations, I think all the three equations are the same conversion, which is the level is not stationary. Although you refer to the AIC and SIC, so I mean you need to refer to different equations. For example, if SIC, the first equation, okay, none. And then SIC select or suggest the second equation, but all the equations are the same. The p-value greater than 0.05. So we do not reject, conclude that the series has a unit root. Okay, so we need that the series is not stationary plus it has seasonal variation. Okay. So when we apply seasonal difference, how to apply seasonal difference? So in this, if you use, we cannot remember that after you apply the difference, you have to perform your unit test again in order to check the difference series of whether it is already stationary or not. Okay, but we don't have option here. We don't have an option to test for the seasonal difference because it just only allow us to perform the test on the levels per different second difference. So we don't have seasonal difference here. So you need to generate or create the series of the seasonal difference series. Okay. So you cannot perform the test here. So you have to generate the seasonal difference series and then perform the test on that different series. So you go to quick generate series. Quick generate series. Now let's say we name the new series as seasonal difference of the electricity data. Actually, the series are already given here, but I just show you how we create the series. So let's say we name the series as ST, seasonal difference of electricity data. So you just use D. D bracket the name of the series, and then you put 0 to 12. Okay, so the first one refers to the non-seasonal difference. Second refers to the seasonal difference. Okay, this one, the second one, the first one depends on if there is no non-seasonal difference, the difference between two values, two successive values, then put 0 if you want to apply seasonal non-seasonal difference. One of the non-seasonal difference, you put 1. If you want to apply twice of the non-seasonal difference, you put 2. Okay, and then this one is seasonal difference. So the value depends on the frequency of seasonal frequency of data. If you have monthly data, you put 12. If you have quarterly data, you put 4. Okay. So this one represents YT minus YT minus Y. YT minus YT minus S. So your S here, you need to put your S. If you have monthly data, you put 12. Okay. And this. You cannot, if it is too small to see, then you can refer to this one. You can refer to the this the word file that provide here SD. This one it's up to you whatever name you want to use, but this one you have to use command D bracket the name of this comma 0 comma 12. Okay. So okay. So we have this one. Okay. So we don't have the first 12 observation because it is YT with the difference between the same month this year and minus the previous month. Okay, the second year minus the first one. So we don't have the first 12 observation. So you inspect the graph. Okay, you see the graph of seasonal difference series. So now you need to perform tests on the seasonal difference series. Okay, so you need to perform tests again in order to decide whether further differencing is required or not. Okay, whether it still has to be root or not. So you perform the test here, just like before. So, but this one because we apply the test on the seasonal difference series. When you perform the test, you select level. Okay, you select level because we are conducting the test. We are implementing the test on the seasonal difference series. So we select levels. Okay, level. So you get the result. So you recap back to the word file, seasonal difference series. You apply the 3 equations of the AF test. So this one is none. The first equation, so it's just the series, the different series, the difference ST elect, the seasonal difference series, still not stationary because the P value greater than 0.05. Second equation is less, it's stationary, and then based on the second equation, the third equation also the same, less than 0.05, but the one that has smallest AIC and SIC, the second equation. Okay, second equation has smallest AIC and SIC. So if we make conclusion based on the second equation, then we can conclude that seasonal difference series already stationary. No need to apply for the differencing. Okay, if we perform if we make decision based on ADF test. However, if you perform KPS test, then you may make different conclusion. Okay, if KPSS is one, KPSS. So how to perform that one I already explained last week. So this one I just showed the result. I hope you already know how. I mean, the same this one. So ADF, KPSS, that's one, KPSS. And then you perform the test KPSS, but we have the equation. Intercept, try and intercept. Okay, but you want to test on the seasonal difference series, and then you just perform, you select level because we are conducting or we implementing the test on the seasonal difference series, not on the original level, but on the seasonal difference series. So if you get the result for the KPSS test, so this one KPSS, KPSS test. If we perform the test on the levels. Okay, on the levels of the series, original series and then this one greater than this, you perform the test of 5% level. Because the KPSS we don't have P value, we only have critical value, test ST and critical value here. So you compare test ST and critical value at 5%. So normally we 5%, normally we 5%, but you also can use different significant level. But I mean, in exam we just use 5%. If not, if the equation does not mention, if equation mentions to do different significant level, then just follow the instruction. So this one, the null hypothesis, this one, null hypothesis that the series is stationary, alternative not stationary. So your test size state greater than critical value, so we reject, conclude that the level is not stationary based on the first equation constant. Second equation, constant linear track, constant and linear track. This one also character, statistic character kan. So this one also the same. Conclusion level is not stationary, and then we apply signal difference. So now remember now because it is not stationary, plus it has signal variation, so we are encouraged, although it is okay, it's acceptable, it's not wrong for you to apply non-signal difference. Okay, if you decide to apply non-signal difference, okay, fine. But you are encouraged or recommended to apply seasonal difference first. Okay, if the series has seasonal variation. So we apply seasonal difference, and then we perform the test again on the seasonal difference series. Okay, the first equation is already stationary. Second equation not stationary, but the second equation has smallest EIC and SIC. Okay, second equation has smallest EIC and SIC. So meaning that based on the KPSS test, KPSS test, if you want to have stationary series, it is suggested that we apply further differencing. Okay, but further differencing, for the second difference, you apply non-signal difference, don't apply signal difference. Signal difference only once. Only apply signal difference once. If the series requires further differencing, then apply non-signal difference. Okay. So to apply both signal and non-signal difference, so let's say you want to see the value. So non-signal difference, let's say this one is the value of signal difference. This is the signal difference. So to apply further differencing, you apply non-signal difference by taking difference between two values, two successive values. So this one minus previous one, this one minus previous one. Okay, so that can be done by if you generate series, you go to quick generate series, and then let's say you name the series. Let's say you apply both difference, and you name as this one the difference, non-signal difference of the signal difference series. Okay, is that given in the word file? So this one, this. Okay. So you apply. Now you want to apply both non-signal difference and signal difference. So you put the name of the D bracket, the name of the series, comma 1 for non-signal difference, comma 12 for the signal difference. Okay. So you click OK. Now you check your this one. So you have this one. Okay. For both seasonal and non-seasonal difference series. Okay, so now you need to apply the test again. So you, in order to perform your test again on the different series, you can either perform here or you can perform here. If you perform here, you select level. If you perform here, you take not here. Okay, this one. Okay, so this one the seasonal difference. If you apply here, this is the seasonal difference before seasonal difference. This is both seasonal and non-seasonal difference. If you apply the test here, you need to choose level. If you perform the test here, you need to choose first difference. Understand? Because this one is seasonal difference. So if you perform the test, you select first difference lah. Meaning that it's first difference of the seasonal difference. Okay. But if you perform the test here, you choose level. If you perform the test here, you choose level. The result is going to be exactly the same lah. Okay. So basically, not to wait in order to save time lah. So you can just do like this lah. No need to create this one. This one I just want to show you. Okay. So but in the actual step of the actual practice, no need to do this one. You can just perform the test here. So select first difference, okay, and then you get the result. Okay, 0.0198. This one constant, constant. So KPSS. Okay, this one ADF. You perform test KPSS, huh? Okay. So based on this, after we apply both seasonal and non-seasonal difference, the test statistic smaller than critical value, and then the first equation has smaller value of AIC and SIC. So if we conclude based on the first equation, then this one, the seasonal plus non-seasonal difference, the different series after we apply both seasonal and non-seasonal difference already stationary. Okay. So the second equation also cited the same conclusion, but this one has smaller value of AIC and SIC. So depending whether you make the decision based on ADF or based on KPSS or based both. If based both, then to be safe, it's better to apply predicting. You take into account the result of both ADF and KPSS to be safe. Then you can apply for the differencing. So if they say you just perform you make conclusion based on ADF test, and then you make conclusion that the seasonal difference is already stationary, then you can identify possible AR or NA model by looking at the program of the series. Okay. So you have to first decide what is the order of differencing, and then after you specify that the series is already stationary, then you identify possible ARMA model AR or NA by looking at the programs of the different series. Not the labels, so identify model by looking at the program of the different series, the series that already stationary. So if let's say you perform the test based on ADF and you conclude that seasonal difference is already stationary, then you can identify model by looking at this now. Okay. If you conclude based on ADF, you apply both different non-seasonal and seasonal difference. And you identify model by looking at the holograms of the for the both seasonal and non-seasonal different series. Yeah. So this one just explanation. So the different series present a change in the elasticity production between months of consecutive year. The difference is now much closer to being stationary, but it's not absolutely stationary because you look at the graph. You see in terms of the mean. If you perform the test, maybe it suggests it's stationary, but by looking at the graph, it's not. It does not really certify the first condition, the sample mean, because the mean here is not really the same to the mean here. You think something mean, okay? So if you apply the differencing, then you are able to get more stable mean, okay? So the similarity is also much less obvious, although still present as shown by spike. Like 12, 24, and 6 in the PCF for the case of seasonal difference, this one. So to achieve an absolute stationarity, then non-seasonal difference can be applied. So we apply both seasonal and seasonal difference, and then we get this one. And then you identify possible model by looking at the pattern of ACF and PCF of the differences. So now the model you can extend to include the seasonal component as well. So the ARIMA notation can be extended to handle the seasonal component, and the general shorthand notation is ARIMA PDQ. So this is what we discussed last week. ARIMA PDQ. So D represent how many times you apply non-seasonal difference. Okay, non-seasonal difference just between two values. And then the P, small p for non-seasonal AR, small q for non-seasonal MA, moving average. And then we have a component for the seasonal component, large D, how many times we apply seasonal difference. Okay, and then P is the order of seasonal AR, Q is the order of seasonal MA, moving average. And then S is number of seasonal frequency. So you have monthly data, S is 12. If you have quarterly, S is 4. So mathematically, we write the equation like this. So previously we have this one, non-seasonal AR, polynomial, and then we have non-seasonal MA, up to Q, the order Q, and then we have non-seasonal difference, 1 minus L. So today we have seasonal difference. Okay, how many times we apply seasonal differencing, and then we have seasonal AR component, and then seasonal MA component. So for example, if you have, let's say you have ARIMA 111, 111, so you have AR1, non-seasonal AR1, 1 minus P1, L, and then you have the first order of seasonal AR, so you have this one, 1 minus, we use slightly different symbol, okay, the large P, and then L4, because it's quarterly data, if you have monthly data, you have 12, okay, and then seasonal difference, non-seasonal difference, then you have seasonal, non-seasonal MA, seasonal MA. So note that the constant term has been omitted for clarity if yt is replaced by yt minus mu, where mu is the mean of the y values, then a constant term would ultimately appear on the right hand side of the equation. So please take note that refer additional note for the actual equation used because the one that we have here is actually simplified equation. Okay, the one that we have in H naught is considered as, we can say it's a simplified equation, but the actual equation used by use is given here. So I might use. Okay, so basically the use two equations. So the first equation for us to specify the number of differencing, and then we have what we call that the mean appears on the right hand side equation instead of here. Okay, and then we have the other term for the first equation, and then second equation we have equation for the other term, and then here basically we specify the seasonal the component of the AR and MA. So basically this one is equivalent, the one that we have equation, this one is simplified equation, so that we only have one equation after we combine. If you combine this equation, then you get the same. Okay. So for the all model that we discussed earlier in the previous lecture, if you rewrite the equation and then you combine, like something like this, you combine the two equations, you will get the same to the one that of the equation given in the lecture. This one is simplified. Simplified equation, we have one equation. So we combine the two equations and form only one equation. So this one is all for most of the cases. For most of the cases, this equation is equal or similar or equivalent to this one, except when we have this. Okay. When you apply differencing, whether non-seasonal difference or seasonal difference, plus you have non-zero mean, and then you are no longer able to use this equation because this equation is no longer correct if you use okay, but if you later I will show you basically other software when we apply differencing, then it will only consider model with zero mean. So that if we apply differencing and there's no model with zero mean, there's no mean, then we can use the simplified equation. Okay, however, that does not happen in use because this is actually the original equation used by use, meaning that when we apply differencing and the model has non-zero mean, then we still have constant. Okay, we still have model, we still can have the constant of the mean in the model. Okay, so this one, so just remember this one. If let's say, okay, now certain software when we apply differencing, it will only consider with zero mean. Why? Because, for example, this one, let's say the series has non-zero mean. Let's say, so we use this one in the model equation. Based on this equation, we use yt minus mu. But if we apply differencing, let's say non-seasonal difference, so what happens? So when you multiply, you get 1. So you can see that negative mu plus mu. So the negative mu cancel out positive mu. So certain software like R, when we apply differencing, then it will only consider model with zero mean, without mean. Okay, but this does not happen in the use because the use different equation. Okay, these are actually the equation used by use, which is equivalent to this one, except when we have this. When we apply differencing and we have non-zero mean, then you no longer able to use this equation. You should use the original equation given here. Okay, so I mentioned just now, certain software like R, I can show you. Let's say this one. So in R, this one I will provide basically to be discussed in the last lecture, lecture 14. But maybe I will give you the recorded explanation for you to watch. How to use, basically how to implement ARIMA model in R. So in R we can use ARIMA function that is available in forecast package. So if you use this function, you see, you read the description of the function, ARIMA function. So we do have what we call as the mean, whether you want to include mean or not. Okay, include mean or not. So mean means that you have C. I mean, just like you have C in use. When in use, when you estimate ARIMA model, you put C. That is for the mean. C. Remember, C in use give us estimate for the mean. Okay, mean for model with non-zero mean. So you put C in use. So in R, then you have to mention, okay, whether you want to have the mean or not. Again, okay, and then you read here. This one says that to include mean or not. Should the ARIMA model include a mean or interceptor? The default is true for undifferent series. So for this series, if we do not apply differencing, then it will include the mean. So that meaning that we have a model with non-zero mean, and it is ignored for ARIMA model with differencing. Okay, so in R, if we apply differencing, then we will only consider model with zero mean. Okay, why? Because this one I can tell you, because based on this equation, if the series fluctuate around non-zero mean, then yt minus mu will replace yt with yt minus mu. So you multiply the differencing operator on yt minus mu, it becomes like this. Okay, so this negative mu plus, because the the differencing operator on L doesn't give any effects because it doesn't have any subscript. So L on yt become yt minus 1. L12 on yt will become yt minus 12. But L on mu, it doesn't have any, does not make any change, because the mu, it does not have any subscript. So this one I mentioned before, certain software like R, certain function, for example, like ARIMA function in R, when we apply differencing, then we only consider model with 0 mean. Why? Because this one, okay, because it's considered that after we apply differencing, and then we have positive, negative mean plus positive mean. So this one cancel out this one. Although in R, if you want to include mean, then you can put true. If you still want that mean, just like in use, then you can put true. Okay. But the default one, it says that if you apply differencing, then you will only consider model with 0 mean. So again, if you use, if you have this, you apply differencing, and then the model has significant mean. C is significant. You put C is significant. Then, in order to write the equation, to write the correct equation, then you have to use this equation, not this one. This one is simplified equation. This one is simplified equation. So this one is equivalent. This equation is equivalent to this one, except when we have this. Okay, when we have this, then you no longer able to use the simplified equation. You have to use the actual equation used by Euclid, which is it's written in two equations, and then you can combine. So let's say example given here, let's say this ARIMA 0, 0, 0, 0, 1, 1, then so we have differencing, seasonal difference, and then non-zero mean. And then second equation, we have seasonal MA1, and then you combine with this one. So meaning that we still have mean in the model. So unlike if you simplify equation, then that mean already eliminated because negative mean plus positive mean, so it cancel out each other. Okay. So now step for model identification. First step, determine seasonal differencing order, the large D, and then second step, determine non-seasonal differencing order, small d, and then after you have already decided how many times you need to apply seasonal difference, how many times you need to apply non-seasonal difference, and then you can now identify possible or potential AR or FA model by inspecting the choreograms of the different series. Okay. Then identify small p and q, the non-seasonal AR and non-seasonal MA. Okay, and then after you identify, so normally this one we just inspect the first few leg. Okay, we inspect the first few leg of the choreogram. So let's say this one. Let's say the example that we used before. So let's say based on KPSS test, we suggest that we need to apply both seasonal and non-seasonal difference in order to achieve sessionality. And then, so we need that your dash D equal to 1 . So the first step, identify your large D. So because the series is found to have seasonal variation and it is not, the level is not stationary, so we decided to apply seasonal difference. So our large D equal to 1. And then second step, identify the order of the non-seasonal difference. If based on ADF test, we suggest we don't need to apply frequency 0, right? If based on ADF, as now for this example, because ADF suggests that seasonal differences or already stationary. So no need to apply for the difference based on ADF. And then you identify small p and small q. So based on ADF, let's say you say that seasonal difference already stationary, then you just inspect this one. Not inspect this one, inspect this one. Okay. So for the small p and q, we just inspect the first few leg. Okay. This one for the non-seasonal. For the non-seasonal, the first, just like how we did before. Normally we just inspect up to displacement 5 or 6. Okay. If we have quadrilateral, normally just up to 3 because 4 already seasonal. Okay, in quadrilateral 4 already seasonal. Okay, so just up to 3. But for multilateral, normally we just limit our model P and Q. The maximum we just allow maximum up to 5 or 6. We decide okay, whether you want to up. You look at the previous example that we did in lecture. For example, certain example we just put maximum 3. For example, just example But in order to allow for more possible model, then you can set the maximum order of 6 for both P and Q, and then you just inspect the first 6. So if you look at the first 6, what model we can suggest? MA or AR? If you consider this as exponential decay, and this one is spike at like 1, 2, 3, cut off to 0, then suggest AR3 Then, because this one you cannot, because this one you cannot suggest MA11 too many already. Okay, so you consider this as exponential decay. Then you see this one, the last significant one is at like 3, so you can suggest AR3. So AR3, P equal 3, Q equal to 0. Yeah. Now we expect a seasonal one. So for seasonal component, as AR and MA, how? Basically it's quite similar. It is similar to the non-seasonal one, except that we need to inspect at leg equal to S and S times 1, S times 2, and so on. Okay, for example, recall that if MA1 the theoretical ACF is spike at leg 1, cut off to 0. This one ACF. PACF theoretical PACF for MA1 is decreasing, right? At leg 1, 2, 3, 4. This one and PACF. Example of MA1. How about is SMA1? This one you understand, right? This one we discussed before. So the theoretical, you look at the table that given in lecture 7 for MA1. Theoretically, the ACF spike at MA1 cut off to 0. The ACF exponential decay. Okay. For SMA1, let's say SMA1 and the S equal to 12 months later, and 12, then you have to inspect at leg 12, 24, 36, 48, and so on. So 12 S, then S times 2, 24, S times 3, 36, S times 4, 48, and so on. So you have to inspect and let 12, 24, 36, 48, 60. So the same here, and then 12, 24, 36, 48. So if you are able to see a similar pattern, just like anyone, but and let S and S times 1. Okay. So you are able to see, for example, this one, ACF, it is non-insignificant. Theoretically, it's supposed to be non-zero, spike at leg 12, and then cut off to 0 for other legs, 24, 36, 48, 60. And then PACF exponential decay at leg 12, 24, 36, 48. Okay. For the case of quadrilateral, if quadrilateral you have 4, 8. If quadrilateral, you need to check at leg 4, 8, 12, 16, 20. Okay. For the case of quadrilateral, one example is we have a multilateral. For the case of SAR, also the same. If SAR1, then this one PCF, this one ACF. Yes, the change, the opposite. So recall that AR1 is PACF spike at 1 cut off to 0 is ACF decreasing exponential decay. Okay. For the case of SAR1, seasonal AR1, for the case of multilateral, the theoretical ACF is given like this now. So meaning that the PACF is supposed to be spiked at 12, then cut off to 0, and other leg 24, 36, 48, 60, and then exponential decay at leg 12 ACF, exponential decay leg 12, 24, 36, 48. So for the data that we have before, so this one, okay, not this one, because this one, if we make decision that the series only requires 4 seasonal difference, then you have to check, you have to inspect the holograms of the seasonal difference series. Okay, so this one. Hologram, you go to, so this one is seasonal difference of legacy data. So you go to view, diagnostic hologram, level, not different level. Okay, and then you check. So normally for the seasonal component, we only consider this one we don't want to have too many components, so you can also limit the seasonal AR and A either to order 2 or 3. So meaning that you check if your multilateral either 24 or 36. Okay, we want to include too many. So this one you inspect, let's say up to leg 36. So leg 12, which one significant? PACF significant. And then 24. Significant, 36 also significant. So meaning that we can propose SAR3 here. Okay. So because spike at leg 12, 24, 36 for the ACF insignificant or insignificant, 12 this one insignificant, 24 insignificant. So if we consider the ACF is the one that exponential decay, the true one, the true ACF exponential decay, the possibility of exponential decay, and then spike and leg 12, 36, 34, 36 for PACF, then you can suggest for you can suggest for SAR 3. So meaning that large P equal to 3 and then large Q equal to 0. Okay. So to estimate the model, you can estimate model in use using this command. No, this one. This one. Okay. So you need to type the dependent variable, which is the seasonal difference, space C, and you see whether C is significant or not. If C is significant, then in order to write the fitted equation or estimated equation, you have to use the original or actual equation used by to estimate the model, you can type this one. So you have C, so AR3, so you have this one, AR1, AR2, AR3, and then SAR3. Okay, SAR3. So in ABUs, you need to specify the S. So you cannot put SSR1, you cannot put SSR2. You have to put, if monthly data, put 12, 24, 36. If you have quarterly data, you need to put 4, 8, 12. If it's SSR3, okay. Depends whether you have quarterly or monthly data. So if this one, you estimate the model, quick estimate equation. Okay, so you can name delete. Okay, this one. The previous one just for the test position function. Yes. So you can see the mean, the estimate of the mean C is significant. So you have to keep the C, and meaning that if you want to write equation, you have to use the equation, not the simplified one. Okay, you have to use this one to write the equation. Because C is significant, you have to retain C. Okay. So if you don't want to have C in the model, so that you can use the simplified equation, one other possible way is by applying for the differencing in order to make the C to be insignificant. And then if you don't have, no longer have C in the model, then you can use the simplified equation. Okay, because if you do not apply, if you apply differencing but you don't have this, you don't have mean, the mean 0, and then you can use either one. This one you also can. If you write this one, it's going to be exactly the same to this one. Okay, so this one is not the same to this one only if you have this condition. You apply differencing plus you have non-zero mean. Then the two equations simplified and the original one is no longer the same. If you don't have this, meaning that you apply differencing but you don't have mean in the model, then you can use either one because both are the same. If you combine, let's say you write equation using this one, if you combine the two equations, then you get the same, just like this one. Okay, exactly the same. So this one, you can perform the test as usual. You can perform this one, the stationary test, mass structure, table for example, or graph. But this one, it is easier to check the graph. So the graph says that it is stationary, okay, and then residual diagnostic. So this model adequate or not? It is an acceptable model. Some less than 0.05, some greater than 0.05. So you have to perform the test at any particular line. Okay, so you can, for example, in this case, perform the test at the square root of sample size, but do not take this one. You have to take, because we apply differencing just now, you should take the square root of included observation, this one. Okay. So square root 176, but 13. So you perform the test on the residual at leg 13. Okay lah. Just slightly greater than 0.05. But if at 10% it is considered not okay lah. But at 5% okay lah. Okay. But if let's say you decide based on KPSS test, we suggest that we need to apply both. We need to apply further differencing. Okay. And then you need to propose model by looking at this one, the programs of the both seasonal and non-seasonal difference. Okay. So if let's say you identify model based on this, then large D is 1, small d is 1 as well. Okay, now identify small p and q. So it is either, okay, the first few left. It is either MA1 or ER3, right? If based on ACF, it is MA1 or AR3 if you can add the PCF. So you can try both. So you have either 3, 0 or 0, 1. Okay. If let's say based on the parsimony concept consideration, we go for the smaller one. Okay, meaning MA1. If MA1, then this one 1, this one 0. But you also can consider the other possible model, ER3 as well. If ER3, 3, 0 lah. Okay. And then for seasonal one, so this one seasonal difference, you go to view, colograms of the first difference. Okay, first difference of this. So we expect, so we get the same now. Okay, but for seasonal one, leg 12, this one significant, and leg 24, PACF significant, 36, both is not significant. So it's either SMA1 SMA1 or SAR2. Okay, because this one only at 12, 24 not significant, 36 not significant, PHF 12 not significant, but 24 significant, 36 not significant. So the last one is like 24. So you can try SAR2. Okay. And then you can combine. You can consider the combination. So this one, the possible models. So either you combine MA1 and SMA1, MA1 and SAR2, AR3 and SMA1, AR3 and SAR2. So we can have four different combination of model. Okay, but do not combine this in one model. Do not put this MA1, AR2 in the same model. But you can combine this one and this one, this one, this one, this one, this one, and this one, and this one. Do not combine these two. Do not combine these two in the same model. Okay. So you try each of these, and then you identify which one has smallest AIC. If you want to select one model, or you want to select based on forecast accuracy, also can. You just estimate all the four models, and then you can produce forecast, and then you compare forecast performance of the four models. Okay, see which one produce better or the best forecast. So this one, they say you want to select one model, and you have to justify how we select model. If we want to select model based on parsimony concept, we should go for number 1. Okay, because it has smallest number of. So this one there is no C because C is not significant. Okay, so C is not significant, meaning that you can use simplified equation. C is not significant, then you can use both, either one. Okay, but easier to write using this one. Okay, both the same. Actually, you combine and do the actual equation, and then it just exactly the same. This one is exactly the same. So you estimate the model. Let's say we estimate this model. Arima 011, 011, 12. So grouping estimate equation. So you have to put here both seasonal difference and non-seasonal difference. And then you're not sure about C, you put C and see where it's significant. So MA1, SMA1, and S equal to 12. So C not significant, you can take out. Okay, C is not significant, so you can remove C. So without C, then you can use the simplified equation to write the equation. So this one, you can check the invertibility as usual. Karma structure, table. So it is invertible. Now residual, diagnostic. So all p value greater than 0.05, you can immediately conclude that the model is an adequate model. So residuals are white noise. Okay, so model is valid for for use to produce forecast. Another example. Second example. Okay, right, this one. So the second example, we have this data, monthly data. So figure shows a very clear signal pattern in data plot and a general increasing trend based on autocorrelation. The Boolean signal pattern show clearly, like 12, 24, 26. The evidence just taking signal difference. So we have six data, this one. So what you need to do first, you have to check whether the series has signal variation or not. So that can be done by conducting signal variation test. Okay. So you use command. So you can perform for second example. Okay, second example, you can perform the test just like before, and the result suggests that the series has signal variation, and then you apply in your root test, and then you get to the result that provide in the Word file, example 2 ADF test and KPSS test. So for the case of second data, if we perform the test on levels, the first equation, the first equation has smallest. So basically this one, you get the data, the same data. So sometimes using or make decision based on EIC and IC also not really can produce the best what we call that conclusion, because you get to the graph. Basically it has trend, it has signal variation, but the test suggests that the first equation has smallest EIC and SIC, which is there is no trend, there is no intercept. Okay, but actually there is a trend, and then the second equation you form the third equation. It's not significant, but basically you get to the graph. Basically it has, but because the way that this value on this observation, it makes the test unable to correctly identify that there is actually trend. Okay, so sometimes you have to also inspect the graph as well. Okay, you not only totally rely on the AIC and SIC. Okay. So you should make conclusion based on information from various information based on graph, based on AIC, SIC, but this one you have to be careful. AIC and SIC suggests the smallest AIC is SIC, the first equation, which is no trend, no intercept. Okay, but in this case all three equations suggest the same conclusion. So the p value greater than 0.05, so we conclude that the level is not stationary. Okay. So level not stationary, we need to apply differencing because there is signal variation. The series is not stationary, so we have to apply signal difference. So you apply signal difference just like before. You generate series, okay, and then you apply in your test again on the signal difference series, and then this one, the first equation suggests that it is already stationary. Second equation also the same. The third equation also the same. Although the second one has smallest EIC and SIC, but all three equations suggest the same, that the signal difference series is already stationary, so that further differencing is not required. Okay. How about KPSS test? KPSS test suggests what? So if we perform the test KPSS on the levels, constant the first equation, it is not stationary because greater than critical value. Second equation, it is stationary. Okay. Second equation, which has the smallest AIC and SIC, but the test statistic less than critical value. It is stationary, but remember that this one has trend. Second equation has trend, so meaning that it is trend stationary. Okay, so there is no stochastic trend, but there is deterministic trend. Okay, so you should apply difference. Okay, so when we apply signal difference, I think both equations have the same conclusion. Okay, which is signal difference is already stationary. So you have to identify model by inspecting the program of the signal difference. This one. See the signal difference is, and then you inspect. So this one. So based on the test of LEF and KPSS test suggests that we need to apply seasonal difference, and then further difference is not required. So small d equal to 0. Okay, and then you identify possible AR and MA model by expecting chronograms of the signal difference series. The first few left. Do we have any possible model? It is MA1. MA3. AR all insignificant. This one all insignificant. So MA3 only. So MA and A3. So we have 3, 0. So there is no AR, all insignificant. This one insignificant. Right. Okay, then how about for the seasonal one? Lecture12a. It is either SMA 1. So SMA1 or SAR. So last significant one, like what? 24, right? Elect 24. 12, 24, 36 is not significant, so it's 1. So SR2. Okay, this one. 36 is not significant, so only 12, 24. So you can write program MA3 and SMA1, MA3 and SAR. Say we take SMA1, then we have Q1, this one, 0. So let's say we take the first one. So to estimate the model, this one. So you go to quick estimate equation. So we only apply signal difference without non-signal difference. So 0 at 12, and then C for the mean, non-zero mean. And then MA1, MA2, MA3 for MA3. And then we have SMA1, but in use do not put 1, but put 12 because multi-data. So in use put SMA bracket 12 because it's multi-data. Do not put 1. It's actually SMA1. Yeah. Okay. So C is significant, and we have this. So you can check as usual. Check structure. It is invertible or not? It is invertible, and then residual, and a stick. So all greater than 0.5, you can easily conclude that the model is an adequate model. You can use focus. So to write the equation, you have to refer because it has the differencing. We have differencing plus non-zero mean. Then you have to write equation using the actual equation. This one, this. Okay. So you have to write equation like this. Okay, this one. The two equation and then you can combine. So you can combine, you put this into the first equation, so you get this. Okay, and then from this, you identify your focus equation, and you can use that to calculate focus. So this one you can read, this one the explanation. So we have identified just now the model. After we perform the test, so it is, we don't need to apply for differencing, we just apply seasonal difference. So now we identify P, small p, Q, and large P and Q. So again, just like this step. So we decide to choose the model alpha 0, 0, 3, 0, 1, 1. So this model. So and then you can use focus. So later on we do example how to produce focus for the Sarima, seasonal Arima or Sarima model. Alright, 30 minutes break. We continue at 5 minutes.